technical, long way of how they work, and then we're going to work on developing a shortcut that will work. That's the plan. All right, so let's focus first, since this is such a huge part of this. Real quick though, before I get into this, any questions from homework stuff? Anybody ever try 5-1 stuff out, or 4-9, even 4-7 stuff? No, okay. So this symbol by itself. So this is summation of blank. So it really means nothing by itself. It has to have something in it. It's like a function in a way. The sum of something. So we talked a little bit about this before. If I put the sum, if I put this down, the way to read this is the sum of I squared as I goes from 1 to 6. So it's fundamentally a sum. So it's basically like a function. F of I is I squared. And I'm letting I go from 1 to 6. So what is F of 1? 1. Plus, because it's the sum. Now let I go to 2. So our steps are integer steps. Right? They're normally actually natural number steps, but still. Yeah, so I is 2 next, that would be 4. I is 3 next. I is 4 next.
16.
I is 5 next.
25.
Real quick, have you guys ever noticed how far apart are these?
3. 5. 7. 9.
What are those?
Odd number.
Odd numbers, yes. So real quick, watch. What's 12 squared? 144. What's 11 squared? 121. How far apart are these? 23, right? The odd number. That's basically what we just figured out. This is all side note, by the way. There's certain things you need to realize. What's 11 plus 12? 20 flipping 3. So what's 13 squared? What's 12 plus 13? 25. Add 25 to 44. 144 you get 60 freaking 9, which is what 13 squared is. Alright, so you can think about it on your own later. Is this like you have to know this to be able to survive in math? No. But if you know and understand something like this, you have a little deeper connection with numbers. And there's all kinds of nifty stuff about why this is true. I'm not going to get into that. I'll give you a little hint. Here's 1. Here's 4. Here's 9. Do you see how this is 3 more than 1? This is 5 more than 4. Just keep having to add the same number and then 1 less. Anyway, so that's why they're called square numbers. It's because they make little squares. Alright. Okay. So what do you guys get? Did you guys, anybody do this for me? 30, 55, 91? Maybe? 61? Sure. I'm going to say yes. Okay. So the most important thing then is, if I say this, sum I equals 7 to 10 of I squared minus 4 squared. Can you guys take a minute and figure that out? Okay, do it. Compared to some stuff we've done, this should be like, oh, sweet.
It would be 91 units squared.
Say again?
Would it be like units squared?
Not really, just numbers. So you can imagine them as being little squares, but they're not actually physical. They don't need physical dimensions, they're just numbers. Yeah. Oh yeah, it's gonna be yummy. I just want you to realize that the symbol itself is very close related to what you're going to do. You have to understand what the symbol is asking you to do. So that if you see it anywhere, you know exactly how to break it down. So this symbol says add up things, letting I be 7, 8, 9, 10. So what's the first thing if I is 7? 49 minus 4. 45 squared, right? And then if I is 8, $64 minus 4, 60 squared. If I is 9, 81 minus 4, 77 squared. And if I is 10, 100 minus 4 is 96 squared. And then you just plop that in your calculator, figure out what the hell that is. Too bad. I'm not asking you to do this by hand. 45 times. No. What's important is, do you understand how that became this? Do you like that? I mean, in terms of, does that make sense? If I made you do this by hand, would you like that? No, I wouldn't like that either. Shit. You want me to square those dumb numbers and add them? What the shit? Why do I have this stupid little calculator? So this is not Math 88. You're going to have to assume you could do this if I made you. But just plug this shit in the calculator. What do you guys get? Anybody?
20,770.
20,000?
770.
778?
No, 70. Just no 8.
770?
Yeah.
Okay, I feel like my price is right. Okay, alright. Does the number matter where shit is problem? No, number doesn't matter where shit. I don't even care what's right, to be honest. Plug that something out. The most important thing is how do you go from here to here. So I don't care what I put in here. That's easy, right? Yeah, like it. Just a general note. Does like a function have to have x as an input variable? Could a function have t for time or p for profit or whatever, right? So I could have some I equals something to something. I could have some j equals something to something, and some k equals something to something. I, j, k are normal things that we use for what's called the index. This is the index of the summation. Cool. Like it. Some of you guys have seen summation symbols before. You're a little bit ahead of the game, but they're not that difficult. By the way, I want to tell you, I didn't learn this until way later in my math career, so I'm just going to show you something. This means sum up a bunch of things. Here's what's really cool. Take the pi symbol, make it giant. This means multiply a bunch of things. So if I had this would mean take 1 times 2 times 3. So the sigma notation means add up a bunch of things. Sigma, Greek letter S for sum. Pi, p, product. Anyway, so is that going to come up for us in this book anywhere? Is it going to come up in this semester? No, but it is kind of nice to realize there's kind of this general idea of these capital Greek letters meaning do the same thing to a bunch of separate terms. This means add up a bunch of separate terms. This means multiply a bunch of separate things. Okay, I like it. Okay. Now, let's remember what we did last time. Let's do a quick little example. Let's just do one that we can do kind of quickly, just to get the process down. So f of x equals x. I want to find the area on render f of x from yeah, x equals 1 to 3 using 4 rectangles. So if you missed last class, holy shit. It's a really good one to watch the video. So if I graph this sucker, what's it going to look like? So graph it real quick. Draw a sketch. So kind of give yourself some scale. So at 1 it's 1. And at 3 it's 3. So I want this area. So we're going to do it using calculus. But I really want you to remember the thing we're getting into, this thing called integration, this thing called an integral of something. It's just the area under the curve. What shape is that? Trapezoid, right? Trapezoid is a beheaded triangle. Right? You ever notice it? Die. Oh, poor little Ned Stark triangle. All right. So I could actually calculate this using just basic geometry formula. We're not going to first. We're going to do it with calculus. And then you're like, well, why don't I just use always basic geometry? Or so then what's the formula for that guy? So that's why calculus comes in and says, I got you, don't worry. So it's only certain nice functions that I can use a normal geometric formula for. How often do we have those? Not very at all. All right, so this example we could do. So how do I do this? How wide is each rectangle going to be? Yeah, how do you get that? So that's delta x. It's a symbol for it, right? Kind of makes sense. It's how far you go on the x-axis. So what's the official formula for it? Yeah, b minus a over n. Where n for us is 4. That is the number of rectangles. Ooh, so we said let's use n. So I've got 3 minus 1 over 4. So each rectangle should be 1/2 wide. Like it, and like P. Now, what's the next kind of option we have? Since I didn't really say. Left or right. So the whole idea here is, how tall is each rectangle going to be is going to be dependent on what side I use to designate the height. So if I use left endpoints. First off, let me ask you this. What if I use left endpoints? Oh man. Oh my markers are dying. Are you dead too, little green dude? A little bit. All right. Left hand prints. Left endpoints. So if I use left endpoints, how tall will the first rectangle be? Yeah, because it's going to be based on. So this would be x1. So here's my first rectangle, and it's going to stop at a half. I like it. So here's my first rectangle. Pop. This is going to be an over or an under estimate. Under. So this is going to be x2. So that's how tall this next one's going to be. And this is going to be x3. That's how tall this next one's going to be. And finally, x4. Do I ever use the number 3 for a left endpoint? So that's the mistake people make, is they have one too many rectangles because they're like, it's supposed to go to 3. Well, it does go to 3 because look, bam, it went to 3. I don't need that side. So in symbols, I've got the sum I equals 1. How many rectangles do we have? 4. I equals 1 to 4. F of xi delta x. So this will be sum I equals 1 to 4. Why does this make sense inside? The total area should be the sum of the areas of these 4 rectangles. what's the area of this first rectangle? Is going to be the width times the height. The width is 1/2, it's delta x, and the height is the function value. I mean, that's just let that make too much sense. Sometimes you're like, I can't be right. It makes too much sense. So then I've got f of xi. So it's going to be, where's my thing? So this will be xi, right? F of xi is xi times 1/2. So it's going to be 1 times 1/2 plus,
2 times a half.
careful,
Oh, wait.
1.5 times, so 3/2 times 1/2 plus 2 times 1/2 plus 2.5 times 1/2. I like it. So that would be 5/2 times 1/2. I like it. Go back to my one marker that works good. So I get 1/2 plus 3/4 plus 1 plus 5/4. I get 3.5. Looks like. Does that look all right? Now, real quick, area of this trapezoid. Who remembers the area of a trapezoid? Yeah, it's 1/2 base times height for a triangle, and a trapezoid has 2 bases. Well, how long is this base? 1. How long is this base? 3. And now it's the height. 2. I get 4. That's bad. What happened to me? Are we at half? Oh yeah. Okay, I'm being silly. We haven't. This is the actual answer, right? So why did we get 3.5? Because it was an underestimate. So I'm not going to do the whole right endpoint thing. If we did the right endpoints, I'll bet you some money that would come out to be 4.5. But when you average them, you get the exact right answer. So normally that's an estimate. We only use 4 rectangles. Why did I come out exactly right? Because it's such a freaking nice function. It's not curvy. It doesn't, you know. Okay, maybe. Okay. So let me do this. Should I? No, we're going to do one more thing, and then I'll unleash you on this. Okay, that's very Christmassy. I like that. I don't really mean for that, but it's just the way that. So sometimes in mathematics, the symbols kind of get in your way. This makes it look more difficult than it really is. And why is that? It's not because math is inherently evil. It's because this captures the idea no matter what. But for each individual specific situation, it really is just what's f of x here times how wide is each one, and then go to the next one. That's all it is. All right, so now, how do I improve this? If this was a gross function, how would I make my estimate better and better and better? Yeah, let rectangles get more rectangles, right? Use more rectangles. What I need, I have a few. It needs more rectangles. So if I let the number of rectangles go to infinity, oh shit. That's infinite resolution, right? That would be the TV that you watch 1 second and your mind explodes. Infinite resolution. More resolution than reality. So already got what they want here? Alright. So here's what that looks like in symbols. I just take the estimate of the area see how many rectangles am I using? No. N. Right? So it's like, good job, Jeff. So this is basically for any estimate of an area, this is the formula you use. You said use 7 rectangles. Good. You're going to use this. Where delta x equals b minus a over n. Okay. All right, so now I just add this in. So we're going to do a problem. And in order to do this problem, there are a few things we need to work out first. This is going to involve an urban legend in mathematics. It would not make for a good movie. It's kind of boring, but it's all right. I'm sure some of you guys would have guessed that. So this is what we're about to try to use. Some part of your brain should realize this is not going to be like very straightforward. When I say use 6 rectangles, it's easy as shit. Now we're using an infinite number of rectangles. It's probably going to be a little harder, right? What we're going to need, we will need to know what this equals, for example. What's the sum I equals 1 to end of a constant? Now this hopefully is easy. If I said add 2 8 times, what's the quick way to do that? 8 times 2. So this is saying add C n times. So what's the answer? NC. I like it. So don't look at that like a formula that you're going to memorize. Just go, why does that make sense? Of course that makes freaking sense. It's the definition of multiplication. It's based off of repeated addition, which is exactly what this shit is saying. Add the same thing over and over and over. So what about this dude? This is where we get a little bit freakier. This is where the urban legend comes in. Now, what would this? Let's look at a specific example of this. What?
I think that's what it's before. Isn't like supposed to be like completely counterintuitive? Like you would think it's one like infinity, but it's not at all.
Oh, you need to one after minor jump.
You're, oh god, don't put that shit. People can convince themselves of the weirdest shit. Don't believe everything you see on YouTube. All right, so here's an example. Let's do a concrete example. And we'll develop an idea. This is related to Gauss. I don't think I've told you this urban legend. There's an urban legend. Gauss. You guys ever heard of Gauss? If you take in statistics, the normal curve is a Gaussian curve. The unit of measurement for magnetic field strength is the Gauss. I mean, holy shit. That's the ultimate place to be as a mathematician. When you have a unit of measurement named after you, come on. Sorry. No, I don't want to 5 kilometers. So, supposedly when Gauss was in like grade school, younger age, the class was going crazy, and the teacher said, okay, add 1 to 100, don't say anything until you're done. And he sat down and started reading the newspaper. He's like, I get a little bit of time to myself. This is the story. Nobody knows for sure what's real. So everybody's kind of like, 5 plus 2 is 3. Plus 3 is 6. Plus 1. It's going to take for flipping ever. Little, Gauss was like, screw this shit. What's 1 plus 100? What's 2 plus 99? What's 3 plus 98? 101. 101. 101. How many 101s will I have? 50. You have 100 numbers, and you're going to pair them all up. So it would be 100 divided by 2. That's how many pairs you're going to have. Times 1 plus 100. The first number plus the last number. What kind of sequence does this work for? Any sequence where you keep adding the same thing. So 2, 4, 6, 8, 10, it would work for that, what we're about to do. If you keep adding the same number, this is going to work. And by itself, the result is freaky. Yeah, 50-50. The numbers 1 through 100 add up to be 50-50. That's neat. But let's see, let's capture the idea. What does 100 represent? Total number, and what letter is that? N. N divided by 2 is how many pairs you're going to have. This one, yeah, there's the first term, and this one last term, right? So normally we're going to deal with things that go up by 1. So in general, this would work for, this idea would work if you went up by 2, if you went up by 3. Why are we going to deal with things that go up by 1? Because how do summation symbols work? They step by 1. So we're going to focus on those. So this is the sum I equals 1 to n of I. So if I ever see this sitting somewhere, I can replace it with this. Okay, I like it. I think I'm not going to show you the proof for this, but if you're curious, I could actually give it to you. I kind of worked it out because it's been a while since I did it. But you can imagine the next thing I'd be curious about would be this. Proof is kind of cool, but it takes a little while, and it's a bunch of foiling shit out. It's kind of crazy. That one's definitely not obvious. What I always thought was cool, but I never sat down to figure out, is if, so you see how it's n times 1 plus n over 2 times 2n plus 1 over 3. So I was always curious if there was a mathematical connection there, or if it was just a coincidence. When you do the math and the proof, it kind of looks like it's a coincidence, but who knows? And then you got this guy. This guy is the one that kind of is beautiful, but it throws you off a bit. The sum from 1 to n of I cubed ends up being this guy, the whole thing squared. Which is nice, but also it's kind of like, what the shit? Okay, now right now I know you guys don't understand why we need to know these things. So we're going to work into it. Okay. Questions? So let's try a problem now. So remember, what we're about to get into is finding the exact area. The estimate of the area under f of x gets better and better the more rectangles we use. So if we use an infinite number of rectangles, it is perfect. So let me see, what do I want to use? I think it did one already. Yeah, here we go, perfect, I like it. Can you draw a rough sketch of that for me? Showing some scale. Okay, let me catch up. So the intercepts, if you factor this, is 0 and 2. The vertex has to be at x equal 1, and when you throw a 1 in, you get 1. So this is a very nice little area. Oh, God. There. I want to point something out. If you had to estimate this area, I really, the more this makes sense, you see how it looks like it's part of something that's not quite circular. It's more, it seems like it's elliptical possibly, but the curvature is wrong. But do you see how it's 1 and 1? So if I found the area of that half circle, it should be close to the actual area. If the radius, what's the radius of this weird half circle? Not quite thing. The radius looks to be 1, right? So what would the area be? Pi times 1, so the area looks to be pi. So I would expect it to be around 3.14. Cut in half though, right? So like 1 point, whatever the shit then is, 5/7. Okay, okay. All right, that was just a little side note. You never have to do what I just did. It's just interesting to notice. That's a decent estimate. So if I get something nowhere near 1.57, I would think something's very wrong. Okay, maybe. Okay. So first thing is, what is the width? Well, okay. How many rectangles are we going to use? Infinite number, true, but that's when I take the limit. So before I take the limit, I'm using how many rectangles? N. Stay with me now, come on. I have a handout with worked out examples, so it's nice and neat and all that kind of shit. How do you always find the width?
Oh, right.
B minus A divided by N. You never do something different. It's just that in this case, what's N? N. So what's the width? 2 minus 0 divided by N. So the width is 2 over N. I love you guys. This is a huge thing to realize about math. It should have happened before this class, but if it hasn't, realize it now. The process does not give a shit what I'm actually using. Right? There's a process. What do you do when you multiply things with like bases? What do you do with the exponents? Add them. That's the process. That's the process. Did I say if the numbers are whole? No. Did I say if these are numbered? No. I just said if I have like bases multiplied, I add the power. So what if I have x to the a times x to the 2a? I'd freaking get x to the 3a. See, the process doesn't give a shit what's in there. Because it wasn't involved in the, when you said the process, when I have like bases multiplied, I add the powers. End of process. So it doesn't matter if I have letters of, no, it doesn't matter where shit. So here, what's the process? All right, I do b minus a divided by n. Does it care that n is just n? No, it didn't give a shit. We do. We're like, okay, this is going to be harder. But the process doesn't change. All right, so what else do I need? Remember, we're using this guy. So we got this figured out, right? So the next thing to work on, obviously, is this guy. So I got to first figure out what the hell xi is. All right. So here's the next interesting thing. Doesn't matter if I use left or right endpoints, considering I'm letting the rectangles eventually go to infinity. In the limit that n goes to infinity, what's true about both sides of this rectangle? It becomes the same side. Which is really freaky. Does it ever actually get there? That's the thing about limits. No, but if you pretend like you can get to infinity, the two sides become one. So then does it matter if I use left or right endpoints if they eventually become the same thing? No. In fact, it doesn't matter if I use some random point in the middle of them. Because every point in the middle of this rectangle will eventually become the same. So like if you get sucked into a black hole and you become condensed to a single point, yeah, that's all you right there. Where's my toe? It's right there. Everything's right there. That's morbid, I don't care. So, if I use left endpoints, makes it a little easier to get into this. That's why I wanted to say it doesn't matter what I use. So let's use left endpoints. x1 would be 0, right? X sub I is the endpoint you're currently using to figure out the height. What would x2 be? How far away from x1 is x2? How far away?
It's 2n away.
2 over n. So it'll be 0 plus 2 over n. Do you notice how the fact that I started at 0 makes this a little better? Well, you always start at 0 for problem. Of course not. If it was from 1 to 2, this would have been 1. This would have been 1 plus 2 over n. What's x2? x3.
2.
I'm going to take another step, right? So it'll be 2 times 2 over n. 2 over n plus 2 over n is 2 times 2 over n. So see how this is 2 times 1 over n. This is 2 times 0 over n. This is 2 times 2 over n. So what's xi? What's xi? That's x4. x1 is 0 times 2 over n. x2 is 2 times 1 over n. x3 is 2 times 2 over n. What's xi going to be? Yeah, I made this harder than it really should be, which just sucks for me, but I won't do that. Let me make this a little simpler. It will be just 2i over n. Maybe I wanted to use the other endpoint. In general, xi will be a plus I delta x. So here xi will be 2i over n, because it's 0 to start with. So 0 plus 2i over n. All right, so what is f of xi? What is f of x? What's f of x?
2x.
Yeah, so what's f of xi?
So it'll be 2 times 2i over n plus minus 2i over n squared.
Yeah. So really the two big first things to figure out are what's delta x, and then that tells you what xi is. And then you just throw that shit into whatever functions.
So if it's 2i over n, then why is that 3, 2 times 2?
I know. So all right. So I should have used the other endpoint. So this would have been off by 1. Another way I could do this is say this is x0. I should have used the other endpoint. That's my fault. Doesn't matter which endpoint I use, so of course I picked the wrong one to make this easier. But in general, this is what the xi is. It starts at A, and then you take this many steps. Let me say that again, because that's so cool. You start at A, and you take this many steps to get to the ith one. So then, f of xi is 4i over n minus 4i squared over n squared. Is that cool? Now, I don't give a first shit that this is not, like, exciting. This is not difficult. What's exciting is the fact that you do this process and out will pop the exact right answer. I need you to understand how exciting this is. Is that in a simple shape to find the exact answer? Do we have an approximate answer? Yeah, 1.57. Is that the exact answer? No, this is not half of a circle. The curvature of the parabola is wrong. It's not half of a circle, but it's close, right? I can figure out the exact area of this by hand. And I know that doesn't matter to some of you guys. I know it doesn't, but you got to realize that's flipping cool. I know your calculator can do it. Hey, I want to be able to do this shit myself. All right. And you will have to, so hey, get over it. So now I can just load up. We're bringing it back. Load this sucker up. So here's the one I'm using. It's the main thing about this whole thing right here. Yeah. So then I've got the limit, n goes to infinity. Sum I equals 1 to n. F of xi is that whole thing. And delta x is 2 over n. All right, let me stop there for a second. This is bread and butter shit. This is just plugging stuff in, working it out. Bread and butter. To me, I always found it cool that if you take some time and you set up something that makes complete sense, when you start just cranking and computing and just foiling and shit, out comes the exact answer because you took so much time to develop this stupid thing. The middle is just a bunch of foiling and multiplying and doing limits. and then you get the exact right answer. I mean, that to me is so cool because you took time in the beginning to write something that made sense. So here, this is just distribute. So you get 8i over n squared minus 4i squared, yeah, they're 4. 8i squared over n cubed. Okay. What does this summation symbol care about? What is a variable according to this summation symbol? I is the variable. Is n a variable according to the summation symbol? No, n is the number of rectangles I'm using. It's a set number. So before I apply this, n is a constant, which means I can factor it out. This is just a bunch of repeated sums, like a big polynomial. Can't I factor a GCF out? If there is one, yes. So is there GCF? Yes, there is. Let's do these each separately. Let's see. So you get the sum. What comes out? What does not depend on I? 8 over n squared. And what is this guy? Isn't this one of the ones we just talked about earlier? Yes, that's why, that's 1. Minus, what comes out of this guy? And inside is still this guy. And this is another one of those that we talked about. So then I get limit, and goes to infinity, 8 over n squared. Who's got this written down? This is that one, the Gauss. I don't want to give Euler too much credit. He did too much shit. This is Gauss stuff.
N times 1 plus n all into 2.
Right? That sum is this. It depends on n, but I know I'm going to take n to infinity, and can you already see how that's going to happen? It kicks ass. Minus 8 over n cubed, and this guy was the weird one. Need more room than that, Jeff. N times n plus 1 times 2n plus 1, of course. Divided by 6, of course. Not of course. What's the limit as n goes to infinity of this? You should be able to look at that and just know. What's the degree of the top going to be? N squared. So that limit should be 1. That was close. It's only 1 over. But so that's going to be a limit of 1.
But don't you have to multiply the 8 to the 8 to the n? Of course, you want to do like 8 over 2.
Of course.
Oh,
So that's
what are we
4.
gonna do?
This part is 1, and you're left with 8 over 2.
Oh, okay.
So this is 4 minus. Now what happens over here? What's going to be the biggest degree term on the top if you did multiply? Don't multiply out, dear God. But n times 2n is 2n cubed. Over n cubed is 2, so that limit is going to be 2. 8 times 2 over 6. And what's 4 minus 8 thirds? 4 thirds. Which is 1.33. Is that right? Yeah, 12 thirds, 8 4 thirds. Which, is it close to what we thought it was going to be? Yeah, it's pretty close. Considering our estimate was like, let's pretend this egg thing is a circle. I mean, considering that, that's pretty damn good. Alright, Alright. You're going to hate this next thing. Okay. Alright. The next thing I'm about to do, you never have to do yourself. And sometimes I don't like to say that because then people go, oh good, I'm just going to stare at my favorite wall now. If you haven't already been. But stay with me, my God. I was never shown what I'm about to show you. And then everything makes so much sense that we're about to get into after this. So just deal with it. Alright, here we go. Oh shit. You know, like that's what I do every day. Because I deal with it. So what am I about? So let me see. So everybody got what they want from this. And again, I've got a handout that's going to have all the steps on it, so you can kind of follow it every time you got to do a problem like this in homework. Yes? What's up? Sorry? I'm going to leave this part, yeah.
I should do my camera.
You're fine. I'm going to take that part away. Sort of. Let me see. Let me keep some of this. All right. Let me see if I can do this. Let me see if you guys. You might not even want to write this down. You might just want to watch, which I totally understand. You're like, if I were you, I'm like, I never have to do this. Okay, go for it. I'll watch you. So what I'm going to do is, instead of going from 0 to 2, I'm going to go from 0 to x. So when we first learned derivatives, we actually first did a derivative at a point. And then we said, why don't we just get the function that represents the derivative? And then I can plug whatever I want to into it. So we just did the area from 0 to a point, 2. Or to an x value, with me? So what if I just did 0 to x? Then I'll have a function that represents the area from 0 to whatever the shit I want. You guys semi with me? A little bit? And you're like, why would I do that? Okay. So what's going to change then? Wherever there was a 2, I'm not going to have an x. Right? Alright, so I might want to redo this part. Okay. Does everybody see that? So wherever there's a 2, I'm not going to put an x, because that's what I'm using now. I'm not stopping at 2, I'm stopping at whatever the hell I want to in the future. Same kind of step we did with derivatives way back when. And I've never seen this done anywhere. I'm sure it's done somewhere, but I'm like, why didn't they show me this shit? So I'm doing it for you. You're like, whatever, man. So next thing I need is f of xi, which would be twice x times I over n. The thing is, let me put that there so it's really clear that it's not x sub I, it's I times x. Minus x squared, I squared over n squared. You good? Oh, you're still copying this? Okay. So I'm going to do the exact same thing here now. But now what's going to be here is going to be... This is why you might not want to try to write all this down. Just watch. 2ix, is that cool? Over n? Minus I squared x squared over n squared. Right? The steps don't change. The process don't give a shit that one of the things I'm working with is an unknown. The process is like, I don't know, just plug that shit in. Times x over n. So then, stay with, please, your guy. This is so flippin' cool. So then I get 2ix squared minus I squared x cubed. So when x was 2, that's why there's an 8 here. See that? So we can always recapture what we had before if I let x be 2. So here I get 2x squared over n squared. Here I'm going to get x cubed over n cubed. All right, for those of you kind of still with me. So here I get 2x squared over n squared times this. Here I get x cubed. So here I get, what am I left with here? Oh, I'm sorry, dude. Were you done?
What
No.
was that number where the x cubed is?
What was here?
No, where it's x cubed over n cubed.
Yes?
There was a number there.
It was an 8, because x was 2. Yeah.
Yeah, that's all.
All right. So then what do I get here? I get x squared minus, I get 2 over 6, so I get x cubed over 3. How does that relate to this guy? How does that relate to this guy? That's the anti-flippin' freaking derivative, right? Without a plus c, but why is there no plus c? Because this is from 0 to something. There's no plus c. It's going to cancel, to be honest. Whew, holy shit. So what this does, let me give you a couple things here. what this guy does. I think I did this last time. We took this and we made it a big ass S. Big ass S for something. So we were thinking about, should we use Russian alphabet now? No, let's just make S really long. This becomes f of x. That's related to the fact that it doesn't matter what point I use in the rectangle because they're all going to become the same point in the limit. And then this, in this limit, this becomes the infinitesimally small step that we know so well already from derivatives. And this would be from A to B. That's where I put the from to. Getting used to from to in the summation symbol, and now I just use that same idea on this big ass S symbol. So this is the integral of f of x from A to B.
So on the summation symbol, is it saying like from to, or is it saying like from, and then this is how many rectangles?
All right, wait, say it again, I'm sorry.
Like, n is how many rectangles? Right?
Yes.
So is it saying like from 1 to n, or is it saying like from 1 with this many rectangles?
Oh, I
Or is
see.
it both, or is it like,
Yeah, this I equals 1 means the first rectangle's area. Up to the nth rectangle's area. That's what the 1 to n means. So it is like the first rectangle, second rectangle, up to the nth rectangle. I love it. You see how this doesn't give a shit what A and B are? Because you have to start at the first rectangle and go to the last one. That makes sense, right? Where are A and B in this? It's kind of hidden. Where's A and B in this? Where are A and B in this? Delta x, because that was b minus a over n. That's where it is. It's kind of hidden. It's in there. I was never shown this. So that's what we're about to do. This is not a proof. But it seems as if finding areas under functions is related to getting their antiderivative. In fact, what is x? What was x in what we did before? It was 2. What do you get when you make x 2? Let me do it like this. 0 to 2, right? So we make x 2, what do you get? 4 minus 8/3. That sounds very familiar. No? Yes? And when you make x 0,